I'm going to go right in. Got a lot of good stuff to do today. Let me try something. One last time. Okay. How loud am I? I'm still getting used to these new ones. I only got them yesterday. Okay, you can hear me clearly? All right, let's get started then. Today we will be doing, as I kind of promised you, the shortcut method. It's called the power rule, at least the version we're going to see today, although there's other shortcut methods. All right, there we go. That's about right. So we're going to be looking at but before we get to that, which is step 3, we're going to start by finding the x coordinates of points where a function is not differentiable. And there's 3 homework questions that look like that. We're then going to spend some time creating the graph of a derivative function by using the graph that we're given of the original function, and that's a big chunk of questions. Nothing algebraic going to happen here, it's all visual. And then we get to start at least and find the shortcut, the power rule, in our case, for the derivative function. So that's what we've got today. Let's start with the first ones. When is a function differentiable really becomes when can you find the slope of the tangent line? And a function is not differentiable if you cannot find the slope of a tangent line. So here are some examples. If the function has a jump discontinuity, and let's just say everything's at 3, right? The function is not differentiable at x equals 3. Would you agree you cannot get the slope of the tangent line at that point? Now, what you could get is, I guess, the slope of the tangent line here and the slope of the tangent line there, but couldn't they very often be totally different numbers? So that means there's no unique value. It doesn't exist. Now, you could get a not differentiable for a function that has a vertical asymptote. Well, a couple of reasons for that to be a problem. If it did have a tangent line, there's no point there, right? There isn't a point on that thing, right? Wouldn't it be vertical if it existed? What number is a vertical slope? Well, it's infinity, and we don't like infinity, so it doesn't exist. So vertical tangent lines are not differentiable. So that function will not be differentiable at x equals 3. We know that is a removable discontinuity, and the function is not differentiable there. At least this one has a fighting chance, because you imagine there could be a tangent line there. So what's the problem? The function has to exist for a derivative to exist. For instance, technically speaking, wouldn't I be trying to find the derivative at that point at the top? And you can't find derivatives at points. They don't make sense. So let's move to, well, let's pause for a minute. Have you noticed that every single one of these places where a function's not differentiable are the same places where it's not continuous? And that is true. If you're not continuous, you're not going to be differentiable, right? That's guaranteed. So you might think, well, they're the same thing, so it doesn't matter. No, there are some situations that I'm now going to show you where the function is continuous, but it's not differentiable. Here's the first one. Some functions curve up to a corner point like this one does. You see it there, right at the top of that peak? That function is not differentiable. If you zoomed in and zoomed in, wouldn't there always be a kind of pointy peak, no matter how much you did it? You can't get a tangent line because it's going to be different depending on which side of the slope, right? You're going to have two distinctly different answers, so not differentiable. And by the way, if you're interested, that guy there, the little corner, is called a cusp. Why is that function? For instance, the cube root of x, things like that, end up having functions that have that shape to it. Why is that function not differentiable?
Is it because at 3 the slope is almost straight?
Yeah, it is. It's vertical. If there's any point on a curve where the slope is vertical, I don't know how well I did it, but where my finger is, would you imagine the tangent line would be vertical? It's not differentiable because vertical gives you an infinite slope, and infinite's not a number, so it doesn't exist as a derivative. Although it might look different, this is the same situation. Can you imagine half a circle, right? A function that looks like that. At x equals 3, although you maybe haven't drawn it very well, couldn't the tangent line be vertical? In fact, it would be vertical. That means this function is not differentiable at 3. It's also not differentiable at -3 for the same reason. So these are the places where you do not find values for the derivative. In other words, there's no number that's a derivative, right? Either because it doesn't exist, or it's infinite, or it doesn't exist, or the left or the right is different. For whatever reason, it doesn't exist, and so it's not differentiable. So let me show you some of the homework questions. There's only 3 of them. They're pretty quick. I think they are anyway. Here we go. Here is a graph of a function. It has 2 problems. There are 2 places where this function is not differentiable.
-1, 2.
Agreed. Everyone agree? -1. -1 has a removable discontinuity, and and x equals 2, there's a cusp. Okay. This one has, in my opinion, 2 places where it's not differentiable. One's pretty obvious. Yeah. Would you agree they're a vertical asymptote at 1, and there's a, well, that would be, I'm assuming that's trying to be vertical at 5. And you would write it like this. That's it. Pretty quick. And just for completeness sake, I won't even tell you how many there are. Just tell me the x coordinates of places where this function is not continuous.
-2, 1, and 3.
I heard pretty much that. Agree? Right, let's look at each one. At -2, isn't there a corner, right, a cusp thing going on? Jump discontinuity, and over here, another one of those corner cusp things. That is us pretty much covered what we need in this situation. So are you comfortable that if I gave you a diagram, you know, some combination of these things, maybe stick 2 of them together, that you'd be able to identify the places where it's not differentiable? Okay, check that off my list then. Now, the next thing we're going to be doing is creating the graph of y equals f dashed of x. In other words, the derivative. And we're going to be using it, or we're going to be doing it because they're going to give us the original graph. So, what is a derivative function? It's essentially if you took any function, let's say we got this guy here. I'm going to do a classic cubic looking guy, right? Y equals f of x. We know that at any given value of x, can't we calculate the slope of the tangent line, the derivative? And we call it f dashed of a. Well, can you imagine we just called it f dashed of x? That's what the derivative function would look like. So now I'm going to try and show you, as best I can, how we can do sketches of what the derivative function would look like, even although I don't have any algebra to work with. All I have is a sketch of the original. I can still draw a reasonably good approximation to what the derivative would look like, right? The derivative function. So let's show you some of the processes. If you get a function that is a polynomial, right, a nice curve, then the way you're going to do the derivative is you're going to identify these two key points here. Now, what's special about these 2 points is, won't the tangent line be a horizontal line at the top of a hill and at the bottom of a valley? Now, we know what number you get. What is the derivative of a horizontal line? What number do you get when you have a horizontal line?
0.
0. Horizontal lines are 0. So what you do is you draw imaginary, so pretend these dotted lines aren't there, they're just construction lines, imaginary dotted lines through the 2 places where the 0 derivatives exist. And overkill, I'm going to put 2 big dots. So really right now, don't I know very little, except that the derivative function passes through this point and passes through that point. That's what I know. Now, what that little construction line does is it breaks our shape into 3 regions. I'm going to call them region 1, 2, and 3. Now, in region 1, this is the piece of the curve you've got. Region 2, this is a piece of curve you've got. And region 3, this is a piece of curve you've got. So you've like cut it, right, into 3 bits. And then you focus on each bit. Let's focus on region 1. If we are talking about slopes of tangent lines, would you agree that all the slopes in region 1 are positive, right? They're all going uphill. So I go here and I shade above the x-axis, because doesn't that mean positive derivative? Now, in region 2, would you agree that all the tangent lines are going to be negative slopes? So we shade region 2 and say, oh, it's going to be below the x-axis, right? That's negative values for the derivative. And in region 3, it ends up being positive again. So I am going to draw what the derivative function is going to look like. And it's pretty easy. It has to be here, passes through there. It has to get to here, passes through here, and finish up here. And we make the simplest, most obvious curve that would do that. And you get that. Now, it's an approximation to what the derivative looks like. Agreed? I mean, couldn't that be much lower down? Couldn't it be a bit shallower? Couldn't these be a little bit flatter, a little bit steeper? But the basic shape is one happy face, right? And that's the best we can expect to get in this situation. Are we comfortable with that? Right. So if you got a polynomial, this is what the derivative would look like. I'm making a mess of it. Let's look at another situation then. Suppose you were going to get, oh, I don't know. Try to find another shape. I could do the straight ones. Oh no, let's do this one. This is interesting. In this shape, it's going to come up. Oh, darn it in space. There. There, good. I got to do what I wanted on both sides a little bit clearer. Now, it's not that dissimilar to this shape, but there is one extra thing that I can use that this shape has, but this shape doesn't. So we've just drawn a sketch of the original, and that they'll give us. Let's see if we can now create a reasonable facsimile of what the derivative function would look like. Well, I start the same way as before, and would you agree that there's a hill there and a valley there? So that's going to be zero derivatives. And I do my little invisible construction lines. Technically speaking, when you're finished, shouldn't the only thing that's left be the happy face? So these little extra construction lines and shadings kind of disappear at the end. If you had an eraser, you could do it. Now, again, I have got region 1, I have region 2, and I have region 3. Pretty similar result. In region 1, positive or negative, what's the derivative going to be for any point in region 1? Can't hear you? Positive. So let's try to get all my shading colors going. Positive. Would you agree in region 2? Negative. Region 3? Positive. And then you might think, oh, I'm just going to draw another happy face. Oh, and I forgot to put in overkill points. Definitely there. Definitely there, right? I'm not. I'm going to do something a little different. It's going to look like that. And then it's going to go and do this. Do you see I'm flatlining at the edges? I didn't flatline here. Would you agree these slopes just keep getting bigger? Have you noticed that the curve is flattening horizontally? Now, won't that mean that as you travel along the axis, won't the slope get shallower and shallower? Now, what do you know about slopes that aren't very steep? Aren't their derivatives very small positive numbers? That's what that is indicating. Right, over here, yes, it isn't. It's going that way. It is positive, agreed. But aren't they also getting shallower? And shallower means small derivatives. So do you see the little extra little kink at the tail? So this one, happy face goes up. This one, happy face, and then you curve round because you're going to have to change direction, aren't you? So that you can level off at the end. Right, that's that one. Let's do one more curve one, and then I'll show you some straight lines. And I'm going to pick a very simple looking shape. That's my function. And below it, I'm going to be doing what the derivative function looks like. And I don't have an awful lot to work with here. In fact, there's only one place right at the top. And I know at that point there, we have a zero derivative. If I do my little dotted line going down, you won't see it because the y-axis is in the way. But would you agree that we know that at 0, the derivative is 0, right? Horizontal. Now that means I have a region over here. There's my, I guess I could put a little bit of a dotted line in. There's my region 1, and over here I have region 2. Now what do I know about region 1? All the tangent lines are positive. And what do I know about region 2? aren't all the tangent lines pointing downwards? They are negative. Now I do know something else. The function stops here and here. So I'm going to put construction lines here and here. So that shading should have really stopped there. That's all I got to work with. So we got to figure out what would the derivative look like when it starts off life here, passes through the origin and finishes here. Because the most tempting thing is just to draw some kind of squiggly line. But that would not be correct. So let's look closely at the end. Can you see that the derivative, the slope of the tangent line, is going to go steeper and steeper until theoretically at the end, won't the derivative be a vertical line? Now, what does that look like? Well, vertical becomes infinite. So that tells me that's the shape. Does that make sense? As you get closer to the edge, doesn't the slope either get really big and positive or really big and negative? Any questions about that? So the derivative of a circle or half a circle, doesn't it generate two vertical asymptotes? Which is something you might not have expected. So let's look at straight lines and what derivatives of straight lines look like. And they are quite different. A lot more different than curves. So I'm going to have a straight line, goes like that, and it's going to come down, and it's going to go like that, and then it's going to go up. So that's going to be the curve. Well, I guess curve's the wrong word, but that's going to be the function y equals f of x. And we're going to look at creating its derivative function. Now, when you did, curves, you looked for places where you reach the top of a hill, right? Or the bottom of a valley, right? Because that would be zero derivatives. That's useful. But when you have straight lines, you look at the cusps, the corners. See these guys here? Those are the important places. So you put in your little imaginary construction lines through the cusps, through the corners. But none of these guys, none of these corners has a derivative. So I'm not going to put a dot on the x-axis like I might have done here, right? Not going to do that. These are just ways to separate the original function up. So I'm going to separate this into region 1, region 2, region 3, and lastly, region 4, okay? Now, for each one of these regions, we figure out what the derivative would be. Now, when it's straight lines, it's actually quite easy. What would be the derivative of all the points on a horizontal line?
0.
Be 0. And I'm going to draw a little bit thicker than I might want to. 0. And at this point here, put an open dot. And that's going to basically mean you don't have a derivative there, right? Now you might say, well, it is 0 up to there, but wait a minute, when you look at this side, isn't it a different number? Right, so what's going to happen then in region 2 is that we agree that all these points have the same slope. And isn't it a downward slope? So something like negative 2-ish. So you pick a point here and a little circle here. And all of them are the same number, right? They're all, well, I guess it's negative 3 I've decided there. Now, what about region 3? Well, horizontal. Well, we know how horizontal works. 0 slope. And lastly, region 4, would you agree that all these points have a positive slope? And up here. So when you have a function that is made up of straight lines, do you notice that your answer for its derivative is always going to be a piecewise function, right? It's always going to be broken into little bits, each bit a little bit different, right? But horizontal lines. Are we okay with that? Does that make sense that a straight line function would generate horizontal lines, either zeros, positives, or negatives? You do not get any diagonal lines out of these, because all these points are the same number. If you're the same number, you're horizontal, right? They're all 2, they're all 0, they're all -2, right? They're fixed values. Are we good? Right, and just do a quick scan through. So, curves are curves, straight lines are straight lines, right? They're quite different the way you approach them. So the last kind of thing would be kind of hybrid, and that's going to be a function that has curved and straight line pieces to it. So imagine I get a curve like this and a straight line like that, right? Imagine a function's a bit of A and a bit of B. And this is going to be our original. And we are going to figure out what its derivative would look like. If you're going to do the sketch of the derivative and you've got your original function in front of you, and we tend to look at key points, right? Places where interesting things happen. So for straight lines, wasn't at the corners, the cusps. But when we did, curves, wasn't it where the hills and valleys are. So they actually have a name for these. These are all called critical numbers. So critical numbers of a function are the places where the derivative is 0 or undefined, right? Corners tend to be undefined. Now, in this question, would you agree that there's a 0 derivative there? And would you agree that there's a cusp here? So those are the guys that are going to be the important changeover points. That's places where the derivative changes in some way. Now, at this one here, won't the derivative be 0? So my overkill dot. And at this cusp here, no dot, right? That the derivative's not going to exist at that corner, right? It's not going to exist there. But it still allows me to break up my region into region 1, region 2, in this case, region 3. Now, in region 1, everybody is negative. The slopes are all downhill, so I'll shade here. In region 2, everything's going up the way, so that's positive. And in region 3, all of these are the same number, but they're all negative, so it's going down the way. Now, in region 3, would you agree all the points on this curve have the same number as their slope, right? They're all negative somebody. Let's say round about here. Now, in region 1 and 2, let's ignore what's going on here. In region 1 and 2, don't you have a curve? And the curve has a guy here, negative, 0, a guy here is positive. And the best I can do here would be a fella that goes like this. Now I'm going to go all the way to there, and then I'm going to put a circle. Now, I'm saying that's a thing. Can I do maybe a curve? It's a bit hard to tell, but I'm going for a straight line just because I like it. Have you noticed that there's a jump discontinuity here? So you don't take this guy and then say, oh, it's got to somehow get down to here and join this guy. No, it doesn't. Can't this guy be doing its own thing and this guy down here does his own thing and they never need to meet? So far, so good. Any questions? Right. Almost all your homework questions that involve this give you this picture and they give you 4 guys and one of the 4 guys is going to look like that. So that's how they do the homework questions. That makes sense? That's kind of how WebDesign does it. They give you this, they ask you to sketch its derivative, you do it on paper and then you look at your answer and you look at their 4 answers and hopefully you get to see one that is similar enough to yours to say, yeah, I think I've done it right. Probably I should show you one. I'll shrink this back to some reasonable size. Okay. Here is the original. I wish they didn't put both of them in it. To me, it's easier if the blue bit disappeared, but you know, it is what it is. Here are all the guys. Would you agree that one I just drew fits this picture here? You see the one I just drew? Straight line up, horizontal line, piecewise. Let's see if we can find somebody else. Right, here's a curve. You see it going like that? By the way, right at the ends, would you agree there's also a 0 derivative? So can you imagine what that shape might look like? One of those 4 is the right answer. And that is the end of how do you sketch the derivative function when all you're given is the original. So there should be a drum roll for the next topic. Oops. Finding the derivative of a function by using shortcuts. And we're going to start by showing you a shortcut called the power rule. And we're going to kind of slowly wean you off some notation issues. So let's suppose it was last week and I said to you, I want to find f dash of a, right? Now, we could do it by a number of ways. Let's suppose we decided that we were going to do it using that guy, right? And what it depends, what somewhere between 5 and 10 minutes of some messy algebra, you eventually get the answer, and the answer happens to be that guy. And we call this fella f dash of a. Are you comfortable? You've done a lot of these guys, more probably with numbers here, but apart from that, you've done lots of these guys, and they are very time consuming. So this is a small change, but it's important. We will call it f dash of x is 4x add 4 instead of f dash of a is 4a plus 4. Does that change from this to that? Kind of makes sense, right? And that kind of notation is going to pretty quickly disappear and get replaced by that. So I'm now going to show you by example. Here is a function, and right next door to it, I'm going to tell you what its derivative is. And hopefully you will see a pattern. And that pattern is actually the power rule. So suppose my function was x squared. That guy would be 2x. If my function was x cubed, take away 4x squared, my answer would be 3x squared minus 8x. My answer was 2x to the 4 plus x plus 1. My answer would be 8x cubed plus 1. And if I had x cubed minus x squared plus 3x, it would be 3x squared, take away 2x, plus 3. Original question, what the final derivative would look like. They are not random. There is a connection between this guy and what that guy ends up. Connection between this guy and that guy. So 4x cubed, take away 2x squared, plus 7x, plus 1. If you can see the pattern, you should be able to tell me what the derivative is going to be for this polynomial. 4x cubed minus 2x squared plus 7x plus 1. Anybody want to have a shot at?
12x squared minus 4x plus 7.
Now the harder part. Tell me in roughly English what you did, because it's very often easier to do it than to say it.
So bring up the power. So for the first one is x to the third power and bring it to the front. So multiply by 3 and then minus 1 to the power.
Is that essentially what you were saying to me?
Yes.
Right. That is called the power rule. That's the shortcut. And in general, we would write it in a more mathematical way like this. If you wanted to find the derivative of ax to the n, right? 5x cubed, 4x squared, right? Anything that's a polynomial, then its derivative is multiply by the power and reduce it by 1. That's what I kind of say out loud. Multiply by the power and reduce the power by 1. And if you've ever done calculus before, like in high school, does that ring some bells? Right? Multiply by the power and reduce the power by 1. I think saying in English is kind of easier to see than the formula. Would you agree the formula is kind of generic, but just saying multiply by the power and reduce the power by 1. So we are going to be using our shortcut to find derivatives. So we won't need to do all this anymore. From this point onwards, we're going to be able to do things a lot faster. So just to get into the swing of things. Let's see what we get. Well, multiply by the power and reduce the power by 1. Pretty easy. Multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. And then we have to deal with two special cases. This is one of them. You get a number like plus 5 minus 3, right? When you find the derivative of any number, its derivative is 0. And we don't put plus 0, right? So the derivative of a constant is always going to be 0, right? So if you have an equation and it finishes with plus 7, the derivative of plus 7 is 0, right? Nothing at all. You can basically ignore it, right? Now, the second situation is this one. This one I think a lot of people find easier to understand. Multiply by the power, reduce it by 1. Now, what do you get when you differentiate negative 2x?
-2.
You get negative 2. And that is, and so is this one, by the way, using the power rule. So let me take them in isolation and show you that happening. Here is negative 2x. Let's call it negative 2x to the 1. Now, according to the power rule, you multiply by the power, right, which is 1, and then you reduce the power by 1 to get 0. Well, isn't negative 2 times 1 negative 2? And what is x to the power of 0? It's 1, isn't it? So isn't that the power rule? I mean, it is the power rule, right? So 5x will get you 5 when you differentiate it. Negative 2x gets you negative 2. So I tend to remember them as like special cases. So when I see negative 2x, I just immediately write negative 2 when it's its derivative. Now, what about the number? Well, it technically is the power rule. So let me show you how you might want to look at negative 3, just to convince you that its derivative is always going to be 0, right? Which is how you do it, right? But just to prove that the power rule works. Isn't negative 3 could be written as negative 3x to the power of 0, right? And according to the power rule then, you multiply by the power, and then you reduce the power by 1. Well, negative 3 times 0 is 0. And would you agree that 0 times anything is just 0, so we don't really care about the funny x thing that you get, it's still 0. Have I convinced you then that numbers give you 0 as their derivatives? Where did that come from? There. It's fun. Oh no, that was my earlier question. That's okay. I thought I'd screwed up. I haven't. So as long as someone gives you a polynomial, do you feel comfortable you could get its derivative? So let's move on, and still using the power rule. But we're going to use it with radicals, things like square root of x, and rationals, like 10 over x squared, and 3 combinations of the two, like that. So we are going to use the power rule to differentiate things like the square root and 4 cube roots, 10 over x cubed and 10 over x squared, and you know, stuff that looks like that, right? And for things that are fractions, but the bottom isn't x squared or x cubed, but the bottom is some ugly square root cube root thing. All these situations can still use the power rule, which is multiply by the power and reduce it by 1. Okay, so let's show you how you do that. Okay, and while I'm at it, I'm going to be showing you in a few moments a notation issue. Right, let's take a very simple example. Now, if I want to differentiate a function and I want to use the power rule, I have to get, guess what, a power. So I'm going to call x as the square root of x. I'm going to call it x to the half. Are you comfortable way back in the day that square roots are half powers? You remember that? Cube roots are 1/3 powers, right? And things like that. Now, when you write it as a power, you can use a power rule. So the derivative is multiply by the power and reduce the power by 1. So a half take away 1 gets you negative a half. Are we Cool so far? Multiply by the power, reduce the power by 1. And now we have an issue that you don't like, but it's important, so I push it. And that is style points. WebAssign is not very generous with style points. Well, it actually is. It's very generous. Not good. I guess it has a math problem that it finds it difficult to see what the best version of an answer is. What I mean by style point is, I want your answer to look as pretty as possible. And there are rules for style points. The first rule is make it look like the original. Right, if your original question had a square root in it, your derivative should look like it, right? It should have square roots in it. It shouldn't have negative half powers or even half powers, right? That's the first rule. Second rule doesn't happen very often, but factor the heck out of it. If that really is only going to happen if you have like a polynomial and then you differentiate it and you can factor it, for instance, right? You would be expected to factor it if you can. And the third one, most people hate this one. If it's trig, simplify it. What I mean by that is, can you imagine that you might have differentiated something and the answer ends up being sine squared x plus cos squared x? Shouldn't you call that 1? And if it's 2 sine x cosine x, you should call that the sine of 2x. In other words, use identities. Now, if you're really lucky, there won't be any identities to use. In other words, the answer is what you got right at the start, right? That would be the perfect, easiest situation. But trig does have that step. Most of the time, you're going to be using rule 1, make it look like the original, which means you're going to have to think back to algebra. A negative power is the same thing as a positive power on the bottom. Are you comfortable with x to the negative a half is 1 over x to the half? Right, cover this bit up. Agreed? X to the negative half is that. And then you should be able to say 2 square root of x. So style points is that. Now, homework is going to be really generous, which I don't like, but I have no power over it. WebAssign might take that as an answer and say correct. It should, and it will take that as an answer and say it's correct. And it will take that answer and say it's correct. But that is the real correct answer. These two are correct, but like 90% correct. In the same way that 2/4 is correct, but isn't a half even better, right? It's that kind of situation. And the reason I want to push this, even although WebAssign doesn't, is that in tests, I expect you to do this, right? Exams, I expect you to do this. When you move on to your further career in mathematics, I do not want you to get lazy and think that's the answer, because you go to university and you do advanced math, they are going to kick your butt if you left something like that. Do you already have chemistry professors who'll kick your butt if you don't use the right units? Now, they're not doing that because they're just being awkward. You know, if you don't have the right units, aren't you going to probably screw up something? I do not want to be in a bridge if the engineer doesn't care if it's feet or centimeters. Because if he suddenly does a calculation using the other units, bridges fall down, right? And aircraft crash and all sorts of horrible things happen. Might seem trivial, but if you know, math is very precise. And everybody in the universe says this is the right answer. Even if Web of Science says that is, ignore them. This is the right answer. And get used to doing it that way. That way, it's just going to be second nature, right? You're not going to think about it because that's, you know, that's what you do. Okay, so that is our first example of a radical. Let's up the ante and make it uglier. Oh, and I'm going to do it now. Oops, that's too far ahead. Y equals, yeah, that's better. Instead of calling the function f of x, I'm now going to call the function y equals. The notation when you do that is there, y dashed. Isn't that nice? Notation's not that weird, right? F of x, you call the derivative f dashed of x. If the function is y, you call the derivative y dashed. Now, cube root is going to be called that guy, agreed? You have to write it as a power. Now, multiplying by the power isn't very nice, but you get that. And reduce the power by 1, you get that. And calculus is finished. Now we need to do style points. A negative power becomes a positive power on the ball. Okay, we've seen that. And this is going to test your memory. How do you write x to the 2/3 as a radical?
Cube root x squared.
You're comfortable with that? You'll remember that? The bottom is the root, right? So if that's 5, it's a 5th root. If that's 2, it's a square root. It's 3, so it's a cube root. The top just basically tells you this guy here. So that's 2, it's x squared. And so we now have the cube root of x squared. Now, I'll show you another one. There's an ugly one. I want to find the derivative of 6 times the cube root of x to the 7th. So I'm going to call that 6x. Okay, it's a bit like the reverse of this process. So what does a cube root of x to the 7 look like as a fractional power? Right, there's a 3 and a 7, right? 3 goes one place, 7 goes the other. Cube root x to the 7. What do you do?
7/3.
Yes. So now I can do the derivative, and I'm going to show you yet another notation. So derivatives are called f dashed of x, they are called y dashed, and they are sometimes called that. They're all the same thing, right? It's just different notation, a different label to do it. So let's return back here. Multiplying by the power, 6 times 7/3 actually comes out as a nice number. It comes out as 14. And if you reduce 7/3 by 1, you'll get 4/3. Now, since this is a positive power, I don't end up with a fraction, right? It stays where it is. All I need to do is turn 4/3 into the cube root of x to the 4. Are we good? Are you comfortable with radicals, square root, cube roots, and their derivatives? Right. Now, I'm sure I've mentioned this to people in my class before, but let me try and push why style points are important in mathematics. The one that I like giving you an example of is this one here. What have I just written down?
3 different numbers.
And they can be easily confused based on how messy your writing is.
Also true. And also, you might not be aware of this, probably
Two
you are.
numbers.
These numbers are just different ways of writing the same number, and it depends on which country you live in.
Oh, that's right. I forgot about that.
Look at these two. Have you noticed that the decimal point is in the bottom and the decimal point's in the middle? What does a decimal point in the middle mean to you?
Multiplication.
It means multiplication, doesn't it? And when the decimal point is low down, does it not mean it's a decimal point? So you would look at that as 3.124, and you would look at that as 3 times 124. You see two different ways of looking at things. But that's how I have been writing my decimals since I was a child, because in Britain, the decimal point goes there. You see it's in the middle. Can you see how things get screwed up when people don't agree on standard ways of writing things? Can you see the confusion that could arise when American scientists and British scientists are just scribbling down some calculations and showing each other what they're doing? If I pass that over to an American, he might be thinking, wonder why you're multiplying 3 and 124 if I don't tell you, right? Aren't you going to interpret it differently? Now, do you know who does that for a decimal point?
Germany.
Amongst others. So can you see even more problems when 3 different people get together and start trying to communicate in mathematics? And this is just writing down bloody numbers, right? This is not deep math. Wouldn't it be nice if everybody in the universe, when they solved something or wrote it down, all wrote it down the same way? Would you agree there's a lot of benefit to that? This is what happens when you don't do it. Isn't there a lot of benefit if you do all decide on the style point rules? In other words, don't just leave your answer, wouldn't it be really horrible if Germans always thought that was okay, French thought that was a better way, and Americans thought that was a better way? Every time you wrote something down, wouldn't you have to keep converting it into the other guy's way of doing it to see if your answer was the same as theirs? Can you just see it's not worth the effort? Right, have I flogged a dead horse there, right? I know it's a lot of work. I know it's painful. Sometimes it seems not worth it, but there are benefits, not one of which is everybody in the scientific world has now agreed, at least here. Unfortunately, I think we're screwed. Do you think Americans are going to move the decimal point up to the middle so I'll feel comfortable?
No.
And do you think the French are going to start using the American way of doing decimals to make you feel happy? We're kind of stuck with that one, right? You just got to live with it. At least you're aware of it. Has anybody noticed that when I write decimals, my decimal point does look higher than it usually does? Do you now know why? Now, I really do try to put it in the right place, but it doesn't always work, right? So be aware of that when you look at my notes.
So when they do multiplication, is it just an X or is it just parentheses?
Yeah. You can do it that way with an X, or you can do it that way. That's how we do them back home. So if you wanted to do 3.12 times 4.7, that's how you would write it.
Is that why you write your X's as like a variables so specifically?
Yes,
Mm.
but you get that from school. When I was at school, X's have to be curved, multiplications have to be straight. I know it's you might not notice it, but if you see it enough in Britain, you take it for you know it's a multiplication and you know it's not an X, right? And that's see the things you learn in this class that you didn't want to. But it makes life a little bit more a little bit more, oh, so that's why his X's look funny, or that's why his decimals look weird. Well, let's move on to rationals now. We are only going to deal with very simple rationals, right? We're not going to do, anything like this, right? That's for another time. The ones I'm talking about are just going to be a number on the top with x cubed, x squared, right? That kind of guy in the bottom. And I'm going to use the power rule. So to be able to use the power rule, don't we need to know how to rewrite that as a power? Now you might say, well, it's a power, it's x cubed. Yeah, I know it's x cubed, but it's x cubed in the bottom. I want it to be a power 4 times x to the something. So what does 4 over x cubed look like when you rewrite it as a negative power, essentially?
-3.
-3. And haven't we done this in the reverse order earlier today, right? Negative powers become positive to the bottom. Now, once it's written like that, the power rule kicks in. Multiply by the power, and then reduce the power by 1. And do you notice that the answer is -4, not -2? If you take 1 away from -3, don't you get -4? Simple mistake, but it's easy done. And finish with style points. It needs to look like the original, right? This is the answer, but I want it to look like that guy. So what should it be?
-12 over x to the 4th.
Agreed. Do you agree that looks like the original now? And the guys in Germany and France are all going to do the same thing as well. And we all end up saying, yep, we all got the same answer. We know we've done it right. I'm just nosy and you don't need to tell me. It's totally up to you. Where did the Chinese put their decimal point, or did they use a comma? Does anybody know?
I think they use a comma because I'm pretty sure in Japan they use a comma.
So
Sorry,
commas-
use comma for decimal points?
Say that again. You use a comma for a decimal point. Is that what you
No,
said?
we use period, the dot thing.
Right. Do you put it in the middle or do you put it low down?
Sorry, put it in the middle.
Oh, you're a middle decimal pointer.
Sorry,
That's-
in the bottom. So like 3. It's same as American.
Same as the Americans. Okay.
Yeah.
Right. It's just me being nosy, no particular reason. But that doesn't mean that the Japanese don't use commas. And who knows, if Vietnamese might put their decimal point somewhere different as well, because there's 3 main things, and historically, all sorts of reasons for that. Okay, let's change names. This is not meant to be a big deal. Hopefully it isn't. If the function's called g of x, won't its derivative be called g after of x? Which you can use a notation thing, that's pretty obvious. Right, now, I need to rewrite 10 over x as a power. And a negative power, obviously. What number should it be?
I'm going to go with x. Go with x over 10. Because if x is oh, never mind. It's going to be 10. The power of x is going to be 1. So that's going to make the derivative power.
Oh, you're trying to do too much in one go.
Oh, I see what I'm doing. It's gonna be -2.
Yeah.
Because
Yes.
-1 minus 1 is gonna be -2, so it's gonna be
Right, so 10 over x is going to be 10x to the -1. Agreed? And then what you were saying is multiply by the power.
we're gonna end up with -20 to the -2x.
Well, no, you did too much there. Multiply by the power is -10. And then reduce the power by 1.
Okay,
So you do the multiplication first and then reduce the power by 1 next. So -1 times 10 is -10 and then reduce the power by 1. We agree on that, guys? Multiply by the power, reduce it by 1. Now style points kicks in.
so why does it proceed in that manner? Is it the same? Is it regular order of operations?
Well, the way the power rule works, if I got my power rule written down, I'll do it again. The power rule says if you want to find the derivative of ax to the n, then you multiply by the power first, and then you reduce the power by 1. So the order that you do it is multiply first, reduce by 1 second. And
Okay.
it's not so much the order of calculations, although in the way that sounds right. It's just that's the order that you do it in the power rule, right? The power rule could have been anything, but we've discovered by doing lots of examples, there's a pattern here. If you multiply by the power and then reduce the power by 1, you get the answer, right? Now, style points. What's that guy going to finish up looking like?
-10 over x squared.
Getting a little bit easier the more you do the style point thing, right? Make it look like the original. So far, so good. Right, let's put the package together then. By that, I mean, let's differentiate a fraction where the denominator is a radical, like cube root of x or square root of x in this case. Now, every single question that I've done today has kind of had the same flow. Wouldn't we turn this into a power of x? Now I'm going to do it a little bit slowly. I'm going to call the square root a half. Eventually you do this in one go. 8 on the top, x to the power of half on the bottom. This now needs to become, right, a power. And it's pretty much guaranteed, isn't it, that it's a negative power? And would you also agree it's -1/2? So are you comfortable about how you get from there to there? Right, 8 over the square root of x is written as 8x to the -1/2 power. Once it's right that, the power rule does not care what that number is. It doesn't even care what that number is. Isn't it? Multiply by the power and then reduce the power by 1. So I'm going to multiply by -1/2, and then I'm going to reduce the power by 1, and we get that. And then we're going to do style points. Negative powers on the top, the numerator, become positive powers of x on the denominator. Fractional powers are then turned into radicals. Are we comfortable with that? Now, we've covered a lot of situations in a very short period of time. If I asked you to do that one last week, would you agree that would be a really ugly piece of algebra? you're probably going to have to use the conjugate method. And a conjugate method with fractions. God, can you imagine how much messier that's going to be?
Got a
So,
question.
yes.
Don't we need to rationalize the denominator?
Yeah. Yes and no. No is the answer I'm using. Typically, you wouldn't want to make a fraction with a square root on the bottom. And if the world was perfect, we would have agreed in the world which of those two versions is correct. If I did rationalize the denominator, that would have been the answer. Now, from these two choices, almost everybody, but not everyone, almost everyone, will say that is a better version of the answer. Now, the people who say this is a better version are not wrong, because isn't there a rule that you don't like square roots on the bottom? But there is another piece of the rule. Shouldn't the answer look nice, right? Simplified. In a lot of ways, isn't this one a little nicer looking than that one? So you could argue this is the right answer. You could argue that's the right answer. Most people, not everyone, settles for that. And it becomes even more important to probably leave it like this when your answer ends up being a guy that looks like that. -4 over the cube root of x squared. You do not want to try and rationalize the denominator of a cube root. Would you agree? Cube roots do not rationalize, right? There's no way of making the cube root go away without making the top so really weird that you wouldn't want to do it, right? So if you stick to this, it doesn't matter, right? If you convert it, it doesn't. So that's probably why most people stick to that. But it is correct if you did that. And I don't know if WebAssign is clever enough to know that. It should be. But, you know, I've been proved wrong before. Are we cool? So, it's okay to leave them like that. So next. Oh, how about y equals 10 over the square root of t cubed? Might as well introduce a new variable. There's no reason why x and y are the only guys in town. Okay, tell me what fractional power of t do you get out of a 10 over the square root of t cubed?
-3/2.
Agreed, everyone? 2 in the bottom, 3 in the top. Okay. Derivative, I'll use y dashed. Multiply by the power, which I believe is -15. Reduce the power by 1, and you get -5/2. Style points. Again, I'm doing this in 2 steps. That guy. Would you agree that this answer looks very like the original as well? And we're good to go. Any questions? Do you like the shortcut called the power rule? Would you agree it takes a lot less work than doing it the old way? But we needed to know mathematically the old way, right? The long way, the limit way, so that we could then move on to doing the shortcut. And there's a famous, well, there's 2 quotes by Newton about this type of thing. The first one I like, which impressed me about Newton, is that he was once asked what's it like to be so clever at math, right? To invent things that no one ever thought of. And, you know, he could have went, oh, I'm really good and you're not as good as me and I'm just a genius and, you know, blah, blah. Now, what he said was quite modest. He says, the reason I could see so far was that I was standing on the shoulders of giants, which is a kind of poetic thing. But what he was really saying is he couldn't do half the things he did without the mathematicians that came before him, right? The mathematicians who created functions, the mathematicians who figured out the laws of algebra, right? How you turn things into fractional powers. All those people, he didn't invent that. Other people invented that. He just took what they gave and he added. And I think that was pretty cool. And the second one he gave was a reason for why you needed to do all that limit stuff before you got to this. And I might paraphrase this wrongly, but he went and said, yeah, imagine you needed a ladder to climb up to the top of a wall. You use the ladder to get to the top of the wall, but once you're on the top of the wall, you don't need the ladder anymore, do you? So he was saying, you use the limit stuff to figure out how to get to the top of the wall, right? How to find these things. And then you used the power rule is, hey, I don't need ladders to get to the top of the wall. I now know a quicker way of doing it, right? So the first time I went up the hard way, the second way I took an elevator. They didn't have elevators, but that's the kind of analogy, right? One way you took the ladder, the next time you took the elevator, right? You still end up at the top of the building or the wall, but you kind of needed the first method to make the second method valid.